So I'm not going to dwell on this, but suppose one subdivides the time interval t minus t prime into, say, n equal steps, and then takes n to infinity. Okay, then what happens? We are not good at visualizing infinite number of steps, but it basically will become something like this. So if I start at this point, say x prime, and want to arrive at this point x, this is at t prime and t, then essentially what we are saying is that, because there would be integrals for all these intermediate time steps, spatial integrals, that means that we are going to be, summing over all the intermediate paths, right? So, and as Saif says, k of x t x prime t prime is going to be limit n goes to infinity of d of x1, d of x2, dot dot d of xn minus 1, k, and there's this tiny interval like propagators for this tiny time intervals, k of xn minus 1, tn minus 1, x of n minus 2, tn minus 2, dot 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 dot, k of x1, t1, x prime, t prime, okay? And with a little bit of work, one can show, and if you, I want you to be able to show this, just try it. It's okay if you cannot do this, but, it just like, it'll be good for you to play with this. Also, I'm doing this for the case of the free particle. See if you can generalize it for a more general Hamiltonian, one that, involves a potential. And in the next class, I will give you a clue as to how to do that, okay? So with a little bit of work, you can then show that k, x of t, x prime t prime is given by the limit n goes to infinity. There are integrals over x1 dot 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 xn minus 1, and then there are integrals over dp1 by 2 pi h bar dot 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 dpn 2 pi h bar. So the number of integrals over p is one more than the number of integrals over x, and the integrand is 1 over minus I over h bar. The integral goes from, say, t prime to t, and h, the Hamiltonian, minus p x dot, okay? So you can show this, and this measure, this is a measure, this integration measure is often written in this way. So curly dx of t, curly d p of t by 2 pi h bar, e to the power, so in the limit where n goes to infinity, that's where it's written, e to the minus by h bar, t minus t prime, h minus px dot, d of t. Those of you perceptive will notice that this is the minus of the Lagrangian. And again, going back to the expression where you haven't taken the limit n equals to infinity, you can actually do all the p integrals, and they turn out to be for simple Hamiltonians, where you have a simple p squared over 2m and potential energy, they just turn out to be Gaussian integrals. Okay, so so this is the expression of the path integral. This is the expression of the path integral in phase space. Now, if you do the p integrals, then you can derive the path integral in coordinate space, and that goes from, say, x, to x prime to x, d of x of t, and it's e to the power I by h bar, and then it goes from t to t, t prime to t, and it's the classical Lagrangian, okay, which is a function of x of t and x dot of t. And you sum over, and this is what basically the point, this is where Feynman started his formulation of quantum mechanics, and he derived that this gave rise to the Schrodinger equation. Okay, so what Feynman said was that, if the particle starts at time t1 and x1 and ends up at position x at time t, then to find the probability or the amplitude, we have to sum over all the paths that connect to these 2 points. But each of the path will be, weighted by exponential of the classical of the action. So essentially that gives you a phase, right? So it's a sum over all the phases. Okay, so this is the Feynman path integral. But in principle, all of this just depends on the Markovian property of the time evolution operator. So I just want to conclude, and this is something I just kind of thought that I wasn't planning to do this today. The last moment I decided to do it because I think that this is just such a fun thing and it takes so little time. Like, it just follows from Markovian property, which you've already seen, right? Which you can intuitively grasp. So I just wanted to show you that. So what I wanted you to do is that, can you try to, generalize this, for interacting Hamiltonian. So if the Hamiltonian is, say, p squared by 2m plus v of x, what happens there? Okay, try to do that. And number 2 is, see if you can do, derive, derive the expressions for k, and this is the this is the position space, or this is the position space, or the configuration space. Okay, configuration space path integral. Okay, so see if you can derive the expression for k as a path integral. Okay, so just try it. If you don't have the time, try it after your exam. Try it after during the break in your course, right? If you're a physicist, you should set yourself these goals. Like, I remember that after my undergraduate, I had a little bit of time, and I wanted to rederive special relativity from the single assumption that the speed of light is constant in all reference frames. And it took me a while, but I was able to do that. And it felt, I didn't discover anything new, but this is just like the way that you hone your physics, your physics skills, right? Okay, so any questions so far? Or comments, or the question can be very general before we dive into more mundane things, which we need to do. Okay, so those of you who came late, I wanted to tell you that our our quiz has been postponed until the 27th. And what I'll do is that I will make sure that I post all the lectures until lecture 15, if not more. Well, that'll be very ambitious, but you know. Okay, so I want to shift gears now and talk about real one-dimensional systems, like concrete one-dimensional systems, okay? And we will probably work up to the harmonic oscillator, and if you have time, we will do angular momentum, which is kind of the prototypical, like a proto three-dimensional system.